All right. So I would like to welcome you at this webinar, which is focused on transparent ceramics. And just to briefly introduce the YCN, I think many of you have already heard this presentation a couple of times. So I will just try to go straight to the point and not to postpone too much the amazing talks of our speakers today.
Angle is changed again, and then it's stopped by the polarizer. So this is how you may protect some, for example, beefy lasers from light that could come back. And again, these are quite difficult to produce otherwise, and the transparent ceramics give really nice results. And then there's scintillators, and here a great advantage is not only maybe better properties, but also the possibility to make really big pieces. Scintillators are materials, for those that don't know that allow you to capture and visualize ionizing radiations like X-rays, neutrons, or gamma rays. So what you do, you have usually some kind of sheet or flat part that absorbs these radiations and emits light photons that you can just collect with the camera or with some detector. So those would be some examples of the use of transparent ceramics. But okay, I keep saying this word, of course, because this is like in the title. But what do I mean by transparent ceramics? So when I say ceramics, I mean polycrystalline material. So we're not talking about glass. I wanted to make this clear because this comes quite often. And we're talking about materials that are polycrystalline. So it's also not a single crystal. And the transparent part, in general, what we talk about is, okay, transparent in the visible range. Usually it extends to the near infrared. So if your material is transparent to radar waves, yeah, maybe it's not the standard understanding of transparency. So mostly when you see transparent ceramics, it's in the visible and infrared, so near infrared. And this comes to the question of, okay, can we make any ceramics transparent? Is it just like, is there a trick when you take, you put it into your transparencer super device and then my ceramics become transparent? Well, not really. If you try to ask some of the scientists' best friend, of course, you might get a sentence that, yes, it is possible. So, okay, great. Although achieving, yeah, and then you see that it's tricky, but you might get there. And so just very briefly, this is really no hardcore science, but to explain a few concepts. When you have a piece, let's say flat piece of your material that's polished, and what can happen with light that interacts with it, okay, it can be reflected on the side when it arrives. I have a pointer. Sorry, okay, yeah. So here, if the light arrives from the left side, it can get reflected or it can propagate. And as long as it propagates, that's the part that gets transmitted, and that's what you're interested in. So, okay, you have reflection. Reflection is, in principle, defined by the composition of your material, like really by the chemical or phase composition. So once you know what your material is, you are able to understand what, like, if it reflects and how much it reflects. Okay, it will, and how much it reflects. And if you know the index of refraction, you're actually able to calculate the theoretical transmittance of your material, and that means how much light you can transmit through the material if it is perfect otherwise, okay? Because then there's also absorption. Yeah, if you have any colored piece of glass, it's going to absorb part of the spectrum. So that's something everyone is pretty much familiar with. And of course, the thicker it gets, the more it gets absorbed. And so you have actually less light passing, at least at a certain wavelength. But again, this depends on the composition of the material. So if you know the composition of your material, you're pretty much able to define if, regarding reflection and absorption, it will get transparent. But that's not all, unfortunately. If it was that easy, we'd have a lot of transparent ceramics. because we also have scattering, and scattering is the one that's really inherent to ceramics because it depends on the microstructure. It really depends on how your material was made, not really on as much on its chemical or phase composition. And this is where I'd like to introduce the difference between transparency and translucency. There's been quite a few attempts to quantify that. One very, very nice by, let's say, one of the matadors, maybe, of transparent ceramics, Professor Krell, who wanted to define that as, okay, if the material reaches 95% of the theoretical transparency, theoretical transmission, then it is transparent. If it's less, then it's translucent. And that's quite harsh, you know, because you can have material that you can look through, it looks sort of transparent, and that's the problem. If you don't quantify it, it's really just an impression. But in principle, a good distinction is if you can see through the material at a longer distance. Because if you have material that's translucent, which is here the, let's say, black part with the black border, that's alumina, and it is translucent. If you place it directly on the paper, you can see quite nicely through it. Once you lift it up, everything gets blurry. Why? Well, because you have scattering. And the same happens down here. If we have two similar samples, one that has quite a lot of porosity and the other that doesn't, you actually can see the difference, and that's just by scattering of light. Okay, so as I said, you can, the microstructure is what defines scattering or the transparency. And this is something that we can actually calculate or at least estimate. And if we take a very simple example, let's say one slab of 1 millimeter thick yttrium aluminum garnet, which is one of the typical transparent ceramics, at a laser interesting wavelength of 1030 nanometers, and you have this much porosity. I mean, like, that's 99.999 dense material. That's really dense. You actually don't have any particular effect of pores on the transparency, which is on the y-axis. Once I start increasing porosity, oh, sorry, get away. Okay, already when we get to 99.9, which is still damn dense, for pores in the size between, say, 200 to 200 nanometers to 1 micron, you have quite a big decrease in transparency. And of course, it gets worse. What does this mean? This means that transparent ceramics are utterly sensible to the scattering sources that you have. Because if you look, for example, at thermoconductivity, just one of typical, let's say, material properties that one can be interested in, with 1% porosity, you can have some similar drop of 1.5% in thermoconductivity. That's not really such a big deal compared to a complete loss of transparency for the same porosity. And so, okay, what does this mean for us? It means that we have polycrystalline ceramics, polycrystalline materials, as I said, but since we need to avoid scattering, generally you should need a single phase, because it's very unlikely that you have another phase with the same refractive index, and so that's going to scatter. And another issue are pores. Pores have an even lower refractive index, so they're going to scatter even more than some secondary phase. And probably you will need an optically isotropic material, that is, material that has refractive index that's identical in all direction of a crystallite, because you have a polycrystalline material that is composed of randomly oriented grains, as long as you don't do some magic or science, and this is what happens here. It's just due to birefringence going to scatter, and at the end of the day, that's what you get with this alumina slab. That, okay, I can see through it, but eventually it's just translucent. All right, this, on the other hand, is what you might need. So clean grain boundaries and single phase material without any pores. Well, that's quite difficult, but okay. How you get there, you have to follow carefully the whole ceramic processing. And that's something that DARIIA will talk more about in the presentation. So I will not go deep on everything, also because we might be here for quite a long while. But it means really starting with the powders, going through all the shaping and maintaining as uniform green bodies as possible, and then getting to as dense as possible, right? So when we talk about the densification, that was already in the title at the beginning, it's really not enough to get to the standard fully dense ceramics. Like if you talk to most ceramists and they say, yeah, like my materials actually are fully dense, they are 97% dense. I mean, 97 is pretty good, actually. 99 is even better, and 99 is definitely not enough for transparent ceramics. And okay, where's the trick? How do you get over the missing 1%, right? For this, actually, it was really the Kobler's work that was pioneering and enlightening at the beginning, because what he did was he was very cunning in using the right sintering aid and the right sintering conditions, of course. But the main point is you need to avoid trapping pores inside your grains. You need to remove pores from the material. And if you, for example, reduce grain growth, or if you promote the migration of pores outside, then this is what you're going to get. Okay. And why most of ceramics are not transparent? Because most ceramics are not prepared in the right way, even if they probably might have been transparent. Just look at the standard sintering in air, normal pressureless sintering. That's most likely not going to get you to transparency. Why? Well, because you don't have enough driving force to remove the last pores, even if your material was really good, say, had a uniform and nice microstructure in the green stage. You're probably not going to get complete removal of pores unless you do something more. And that's either you apply pressure, you become really, let's say, nasty on the material, and you, okay, that's not really scientific, but you squeeze the pores out. No, you just, by applying pressure, you really help the removal of the pores. Whether you use hot pressing, whether you use spark plasma sintering or hot isostatic pressing. Another possibility is to use vacuum sintering, where on the other hand, you apply vacuum from outside, you evacuate the green compact, and therefore you have also less air to deal with from the beginning. And another thing that you could do also is the use of a sintering aid. Most likely you will do a little bit of both. And this is just an example of how important the microstructure is, for example, for the use of hot isostatic pressing, which is quite common if you need really high transparency. If you start with microstructure with small grains and pores that are at grain boundaries, by hot isostatic pressing, you might be able to remove those. If already in the pre-sintered piece you have pores inside grains, they're most likely going to remain. They're really difficult to remove, if at all. And this means that, okay, you have to be careful all the way through the process, but really for every step that you do to reach transparency, there might be some optimum microstructure to deal with. And when we talk about sintering aids, I'll just give one example out of really many, because for different materials, you might have different sintering aids that act differently. And in the case of yttrium aluminum garnet, which is a composition that I've been playing with quite a lot, the typical sintering aid is silica, here added as an organic precursor. And you can quite clearly see on the microstructure itself that, okay, if I don't add any, here, for example, I have relatively small grains, but I have pores and the sample is just white, it's opaque. And then by adding more and more of the sintering aid, I, for example, here observe some grain growth, but I see migration of pores, or let's say pores remaining here only at triple points. And with 0.5% of TOS, I actually don't see almost any porosity, and the material is transparent. If I exaggerate, I'm going to have grain growth that's just exaggerated, and I'm going to have pores inside grains. It's not going to be transparent anymore, or it's going to be translucent. And I might start also seeing secondary phases. That means here the process was vacuum sintering. If you use different process, the optimum would be somewhere else. But there are ways to make your material transparent if it can be transparent in terms of, okay, not absorbing, not reflecting. And okay, here we get to the, let's say, main competitors. So you can, in the same type of applications, you can have glasses, you can have single crystals, and you can have transparent ceramics. That's something that I've already shown in the beginning with the examples. And what transparent ceramics bring, and what I see as the main advantage, is the combination of the properties of a crystalline material. That means definitely higher thermal conductivity, better mechanical properties, and the shaping possibilities of ceramics. Because, okay, single crystals, you just grow single crystals and then you go on cutting and machining. In glasses, you have the flexibility, you don't have the properties. So let's have a further look on the shaping part, and in particular on what I see as really a potential game changer for ceramics, or for transparent ceramics, and that is composites in terms of macroscopic composites, not reinforcing for having better mechanical properties, but combining parts that have a different composition. And for example, here, these are some materials for lasers, where you have one part, the one with the green color, doped with the laser ecliphion, and the other part that's not. This actually is helpful in one case because the part without dopant has a higher thermal conductivity, and so you can cool better. In the other, because in this way you can create a waveguide, and there are different applications of composite ceramics or composite materials, for example, for lasers. And there you can make some of these also from single crystals. You just cut single crystal, polish it, bond them, okay, sandwich structure possible. Once you want to go a little bit more complex, you want to introduce some thinner layers, you have to go for something else. And there you have ceramics. If you want to read more, this is really nice paper. I just keep saying that, I think, but it really is a very nice read on the topic of composite transparent ceramics. But nevertheless, I'd like to give you a look on this, because I think that's really one of the important points about why transparent ceramics make sense. So as I said, you could use bonding. You can use bonding also for ceramics, and the results are good. You just cut, polish, put together, bond. But you have many other possibilities also. Let's say just the standard dry pressing of powders. Everyone probably has at least once tried that. When you can actually press different parts into one single piece that has different composition inside, sinter it, and for example here, the composition doesn't differ that much. You're just adding a dopant, and so the sintering, let's say, needs are similar, and it's easy. It might get a bit more problematic if you start with, let's say, more dissimilar materials that are not just, okay, I changed 1% of the whole composition and it's another base. This is something that we addressed in scintillators, where we're combining two different garnets, gallium, gadolinium, aluminium garnet, and yttrium, aluminum garnet. The problem is they can't be sintered at the same conditions. So this gets a bit, let's say, more complicated, because the point is, while yttrium aluminum garnet is happily sintered under vacuum, if you put the other one under vacuum, you have issues with gallium that's in reducing atmosphere. And so you need to find a workaround, but ceramics give you quite a lot of possibilities to do that. a wonderful area it is. And so, okay, we find out that if we use air presintering and hot isotopic pressing, we can actually, by co-pressing the parts first into one single compact, get a composite part that is transparent and works, and in this case allows you to see both X-rays and neutrons. Okay, another possibility that's more for the thin layers or for 2D structures or 1D structures is tape casting, where you produce these thin sheets and you can stack them, thermocompress them at some 100 degrees into these layered parts, and after some debinding, you can sinter them to transparency. And again, here you can play with the composition of the different layers and prepare even graded structures. Another possibility that I think could make sense, especially for larger parts, is slip casting or pressure slip casting, and even some of the really most expensive parts that you can find now for lasers. Some of them were produced by slip casting in the Konoshima company. So definitely, why not? And then the one that's really fancy these days, and I think we might see more and more of these results soon, is the use of additive manufacturing. And also here, I could have another presentation, but we don't really have the time. There are different approaches in additive manufacturing that allow you to produce transparent ceramics, and some of them even to produce composite or graded transparent ceramics. And this is definitely not all. These are, let's say, the most general and clear examples. But okay, I'm actually not sure how I'm going on with the time, but what okay, thank you. What I wanted to show is, okay, this was some general overview of what has been done, what's being done, what could be done in the standard transparent ceramics, so to say. And I gave you some indications on, okay, if you follow this and this and that, your ceramics might be transparent as long as they are not, I don't know, too reflective. Well, okay, those are not all rules, those are suggestions and indications, because for different of those you can find a workaround. And so when Sonia introduced the outside the box idea, I actually thought it might be interesting to have a look at these also, because you don't really have to have a single phase system or single phase material to have it transparent. You don't really need to have clean boundaries to have the material transparent. And it doesn't even have to be cubic or optically isotropic to become transparent, if you know how to work around that. And so when we look at the small grains, I'm sorry, if you look at the single phase or multi-phase systems, the trick is in having small grains, because, okay, here, as long as the grains are relatively big, let's say micron size, you're just going to have too much scattering to have a material that's transparent. If you start reducing the size of the grains, actually what you can see in this graph, or at least I hope you can, on the z-axis, on the vertical one, you have transparency, and you can see that actually from the 0 total opacity, it starts to get up here to some reasonable numbers. And what we're doing here is we're going up with the wavelength, and we're going down with the size of, let's say, scatterer, in our case, of the grain. That means that if you have sufficiently small grains, let's say in the 100 nanometers range, maybe less, maybe more, depending on the material, for wavelengths around 1 micron, you might just easily have material that is at least translucent, if not transparent, sorry. And there's been quite a lot of work on that in the system of yttria magnesium oxide in the last, I'd say, 20 years. And the results are quite nice. And nowadays, there are also other systems where instead of yttrium oxide, you may have gadolinium oxide or some other stuff. The point is, okay, I do have a difference in refractive index, but if the wavelength is long enough and the particle size is small enough, I actually get some transparency. And this, of course, applies to many other systems in principle, as long as they're not miscible. And in the same way, it actually can apply to materials that are not cubic, that are not optically isotropic. Specifically, fluorapatite can be transparent and can actually be a laser host material. And if you prepare it with sufficiently small grains, like the group of Furuse, where you can see, or at least I hope you can, you have some maybe 100 nanometers grain size. Again, the scattering is not that strong, and they were able to get quite nice transparency here. But for this specific material, this is not the only possibility of how you can get it transparent. And the other one is even fancier. Okay, just I might add one comment before, and that is, if you want small grains, often you need to get to not too high temperatures, and that means that you might need to use pressure. For example, hot isostatic pressing, SPS, and you might need to start from small powders, like smaller than the grains. But another possibility for the fluorapatite to become transparent is to produce the green part in a strong magnetic field. Why? Because these particles are actually magnetic. They react to the magnetic field. And so if you produce the part by colloidal methods, when they can really move around, and you apply a strong magnetic field, they can actually align. And then once you sinter them, you can see that you actually get, again, transparent material. So of course here, not every material will react to a magnetic field in the same way. Some won't. But if they do, this is again a possibility on how to make material that otherwise would not become transparent. And another, say the last and the first at the same time, because the first work that was presented and one of the first that I shown you on the materials for the lamps was alumina. Well, okay, alumina has been produced very dense many times by different researchers, by different producers, and usually it's not transparent, even though the density is very high, because you might have relatively big grains and it is material that's optically anisotropic. What you can do is you can reduce the grain size. If you reduce it significantly, then you start to get some transparency. And if you play more with the process, like Dr. Ikesue did here, what you can do is not only limiting grain growth, but you can make the material behave more isotropically by introducing a grain boundary phase that actually acts on the single grains. And as a result, you get material that's actually pretty transparent with really nice material mechanical properties. And what they did was just adding the right sintering aid and then using vacuum sintering and hot isostatic pressing. And from material that in principle is translucent, you get to transparency. Another attempt, although here it was from opaque to translucent, but I really like the approach, was the use of templating oriented grain growth. And in this case, the authors added to fine alumina powders also some particles that had a high aspect ratio. And since they used also production method, in this case stereolithography, that aligned templates. They already had the green part with alignment of those high aspect ratio particles, and they actually, by the use of SPS, promoted the growth of grains in one direction. And okay, that definitely led to an increase in transparency. And then there are many other approaches, but the point of what I wanted to say was, if you go back to the questions that I asked at the beginning, okay, could my ceramic be transparent? Well, maybe yes, maybe it could. Maybe it's really a matter of how you treat it. If you avoid some impurities, if you, let's say, use the right sintering aid, the sintering process, if you start with fine powders, you actually might be able to produce your material in translucent or transparent form, and maybe it could be worth it, because there's quite a lot of interesting applications. But one thing that, at least in my opinion, still remains by the rule is that you need to get as close to 100% in density as you can, because the porosity is the one that scatters the most. And scattering is exactly what you don't want to have in a transparent material. So yeah, you don't want to scatter, but you can control the microstructure and deal with the scattering. And yeah, maybe your materials could also be transparent as ours. Okay, I think that be all from my side. I'd like to thank for the opportunity to be here to talk to you, and of course I also need to thank for the money that we get to work on these topics. Yeah.
Thank you very much, Honza. I would like to ask everybody, if you have any questions, please write them down in the chat. We will have a discussion session after the second presentation. So if there is anything you would like to ask about, just write it down. And for our next speaker, I would like to invite DARIIA CHERNOMORETS to the floor. And just briefly about DARIIA. DARIIA is a PhD student at the Institute for Single Crystals in Kharkiv in Ukraine. But currently she is a visiting student at the CNR ISSMS in MMC, sorry, in Faenza, Italy. And I'm really glad to say that DARIIA is our representative of Ukraine. So one of the very active people within the YCN. Besides that, DARIIA works with yttria-based transparent ceramics obtained by different shaping methods such as dry pressing or slip casting, and also different sintering methods such as vacuum sintering and spark plasma sintering. So that's shortly about DARIIA, and now the floor is yours.
Okay, thank you. Can you see my presentation?
It's loading, so just wait. Yes, we can see it now.
Perfect. So, first of all, hello everyone, and I wanted to say that I'm really grateful to have this opportunity, because I guess like not every young scientist has such possibility to present yourself and his work. So for me, it's a very important step. So thank you everyone for attending, and YCN for proposal. Also thank you for introduction. As Sonia told, my name is DARIIA CHERNOMORETS, and today we will speak about top 3 challenges in transparent ceramics. 1 second. Yes. As Sonia told, I'm a PhD student in Institute for Single Crystals in Kharkiv in Ukraine, visiting student at CNR ISSMC in Faenza in Italy, almost 2 years, and I'm representative of Ukraine in Young Ceramics Network for this and the next year. Well, I started my way in transparent ceramics 3 years ago in Kharkiv. 1 second. Yeah, here in Kharkiv. When I've just come to the institute, it was decided that I will work on obtaining of complex shaped ITRIA transparent ceramics by slip casting. And honestly, in that period, I thought that it will be my main challenge for the couple of next years. But a bit less than in 1 year, it was completely changed. And due to full-scale Russian invasion to Ukraine, I couldn't continue my work in Kharkiv. And in June 2022, I came to Italian Institute for internship, thanks to support of European Ceramic Society and Jack's Trust, and also a group of transparent ceramics in Italian Institute. I've received Jack's Trust mobility travel grant, and my work in Italy was started. When I just started to work in this field, I was sure that I will face only such problems like obtaining of transparent ITRIA ceramics by slip casting, maybe combination of studying and lab work, and of course publishing and presenting of results. But in reality, it was more complicated. It was a combination of some like personal challenges, like adaptation in new country, language barrier, endless searching for accommodation. I guess that every student who comes to new country face some of these problems. And of course, I had still the same issues with combination of studying and lab work, publishing of results, etc. But thanks to nice people here and sunny weather, and of course, super good Italian cuisine, it was way easier to work with it. Now, I guess we can move to challenges which I faced directly in transparent ceramics, but just short introduction to transparent ceramics. We heard a lot about it in previous presentations, so I will not say really a lot here. First of all, it should be mentioned that generally we have to achieve high density of a sample and produce sample without any defects like pores, secondary phases, or impurities. Since presence of any of mentioned defects leads to light scattering, and as a result, deterioration of optical properties. Like here, we see two pictures where we can see translucent and transparent samples and their comparison. And as I already told, it was quite clear, explained before. And here we see influence of porosity on optical properties, and with increasing in porosity, we can see deterioration of optical properties. That's why it's important to follow all these requirements. And the first challenge is the choice of the right raw materials. Why is it so important? Here we can see morphology of two different raw ITRIA powders. Here we can see that they are completely different. Morphology is really different, and we can assume different properties of these powders. The first powder is characterized by soft agglomerates, and it can be easily broken as a result of planetary ball milling. After milling, primary particle size is in nanometric scale, so probably we can expect uniform macrostructure and high density of green body with this powder. With second powder, it's not so easy. Agglomerates are hard with irregular shape, and we can see that milling is not so efficient. So compared to the first case, probably we will have lower density of green bodies with more defects. We obtained samples by uniaxial pressing, cold isostatic pressing, and vacuum sintering. And here we see microstructure of these samples. In the first case, microstructure is uniform and defect-free. We can't see any porosity or secondary phases. While in second case, microstructure is quite porous. So probably looking on microstructure, we can say that the first sample will be transparent, while the second one will not exhibit so good optical properties. And here is appearance of the samples. And as it was predicted, we see highly transparent sample and completely opaque, which is in agreement with obtained microstructure. And some results. This sample is characterized by quite high inline transmittance, which is above 78% at 1100 nanometers, while for this material at this wavelength, maximum is 82.4. So this result is quite close to theoretical, while second one is completely opaque. So here is a short summary about first challenge. First of all, powders morphology effects on their centerability and density of packing. So we will have different optical properties of ceramics, which is obtained at the same conditions as we saw before. Also, it should be mentioned that choosing of raw powders really depends on shaping method. Here we can see sample delamination after uniaxial pressing. It happened because we used quite fine powder. So this powder is not so suitable for dry shaping methods. But at the same time, it's quite good material, quite good powder for colloidal shaping method. So it always depends on your shaping method. To increase the centerability and high density of packing, and to achieve high density of packing, powder should have a uniform particle size distribution. Also, quite often, it's better to have small primary particle size, and as a result, high specific surface area. But of course, it's possible to achieve a high density of packing with quite big particle sizes if powder is uniform. And shape of particles should be close to regular spherical to achieve high density of packing, and as a result, less defects, more uniform microstructure of green bodies, and high transmittance. But also it's important to say that nano-sized particles can agglomerate due to interparticle forces. As a result, it's possible that some defects during pressing can be formed, and centerability of this powder will be decreased. And the next challenge after choosing of raw material is a right shaping method. Here we will speak about colloidal shaping methods and more in details about rheology. Among the advantages of colloidal shaping methods is a variety of possible shapes of final sample. Rheology of suspensions plays one of the main roles in obtaining a desired shape and density of samples by colloidal methods. Rheology includes such characteristics as, for example, viscosity or viscoelastic properties, etc. But today, here we will speak more about viscosity just as example. Slurries or suspensions can exhibit different rheological behavior, and required rheological behavior depends on chosen method. For example, if we speak about slip casting, Newtonian behavior is required, while for 3D printing, direct ink writing, pseudoplastic behavior is required. So if we speak about slip casting, there are some requirements. We should achieve low viscosity, electrostatic and static stability, high solid loading, and Newtonian behavior of slurries, while at the same time we should use uniform powders as it was established before. Simultaneous fulfillment of all requirements leads to formation of uniform green bodies with uniform microstructure and high density. Here we can see example of dependence of viscosity and shear rate on and shear stress and shear rate of ITRA suspensions with different amount of dollar peaks, which is a dispersant in this case. Only one of all of these, all three systems exhibit Newtonian behavior, and with this slurry, quite good result was obtained. Here we can see obtained green body with this slurry and vacuum sintered ITRA ceramics, which is transparent, but here it's not polished since it's not so easy to polish complex shaped samples in our laboratory at least. But even not polished sample exhibit quite good transparency. Now we move to direct ink writing, and requirements is more or less the same, but in contrast to slip casting, we should have high viscosity and pseudoplastic behavior. Why is it important? We will have not only uniform microstructure of green bodies, but also sample can keep shape in this case. There are two viscosity flow curves of yttria-based inks with different solid loading, and in general it's more or less the same, but a difference only in 6% of powder, but viscosity changes really significantly. And manual test extrusion was performed, and we can see that in the first case with 72% of solid loading, viscosity is too low, and this ink is not printable at all, while second one is quite promising, and in general it exhibits quite good properties on this stage. Of course, solid loading is only one parameter which can be changed, and viscosity is only one characteristic. But even here, we can see a really big difference. Now, I would like to show you printing of optimized sample. Yeah. Optimized ink. I'm sorry. And aerology of suspension for colloidal shaping methods is a big and complex part of the process. It depends on type of powder, on solid loading, on amount of organics like 10%, binder, humectant, etc. So, of course, here it's like just an example of a small part of this challenge which you can face working with colloidal shaping methods. But even now, it's clear that it's not so easy. But achievement of required rheology of suspensions leads to dense green body and absence of defects such as porosity. So highly transparent ceramics can be obtained. And that is the last challenge in my presentation, but not the last in the real work. After selection of powders and shaping method, new question rises actually, how to reach full density. And to solve this problem, it's important to choose right sintering method and right sintering conditions, of course. But also sintering aids are important at this step. But the reasonable question can rise, like if it's really necessary to use sintering aids. We will see. There is a variety of sintering aids which can be used in producing of transparent ceramics. And also we can see microstructure of pure and doped yak ceramics with different amount of sintering aid, which is TEOS. So here should be mentioned that not only type of aid should be chosen right, but also an optimal concentration, because we can see that with different amount of sintering aid, we have different microstructure, but only one of them gives us good desired transparency. On this slide, we see my results in obtaining of zirconia doped yttria ceramics as an example. there is a microstructure of pure and doped yttria ceramics obtained by vacuum sintering. Pure yttria oxide ceramics is characterized by quite big grain size and high porosity, and pores are located as in inside grains and on grain boundaries. So in general, just increasing on temperature or sintering time will not be enough to eliminate this porosity. In this case, sintering 8 was used, and we see quite uniform microstructure without defects. At least here we can see them, and with lower grain size. And we can see that transparency, like optical properties, changes very significantly. Zirconium 4+ ions replace yttrium 3+ in the lattice with formation of a solid solution and shown defects. This presence of these ions inhibits grain growth due to partial segregation on the grain boundaries, and grain size decreases, in my case, from 22 micrometers for pure yttrium oxide to 6 micrometers for doped sample, which is quite good result, just taking into account that like it changes only in sintering 8. So using of sintering 8 can have some advantages and disadvantages as every step. And generally, among advantages are possibility to reduce sintering temperature, also reduce grain size. Reducing of grain size quite often leads to improvement of mechanical properties due to hole patch effect. And also promotion of densification is possible. Regarding downsides, possible formation of secondary phases, also quite possible that deterioration of characteristics of laser source or scintillation can be observed, and can appear parasitic absorption visible as coloration. In this case, annealing is needed. Here we can see zirconia doped yttria ceramics obtained by vacuum sintering before annealing, but after annealing it's colorless and transparent. So it's like probably can be one more step in producing of ceramics using sintering 8. But of course, it depends on material, type and amount of sintering 8 and sintering process as like advantages and disadvantages. So we are here again with this question, if it's necessary to use sintering 8. And in general, I can say, no, it's not necessary, because in literature, it's possible to find information about obtaining of transparent material without sintering 8. But it's not so easy to achieve high transparency in this way. Without sintering 8, quite often temperature and pressure of process should be really high, and maybe combination of some sintering methods can be required, which is not available even in every laboratory, and any guarantees that it will work finally, even if you try. And here we have final conclusions about a bit about every challenge. So we start with powders, and powders should be fine with regular shape to ensure high centerability and dense packing. As a result, we will have uniform microstructure of green body, so less defects and high transparency. In shaping methods, if we speak about rheology, obtaining of suspensions with required rheology results in uniform microstructure of green body. And again, it's the same scheme, like uniform microstructure, but like with less defects, so less possibility for light scattering, so we have high transparency. And sintering aids promote densification and allow to control microstructure. So as a result, optical characteristics can be improved. And of course, quite important to say that all of these challenges can't be solved separately. It's part of one big challenge in our field, which is like how to reach this high transparency, because we can use sintering aids, but not write powders, for example, and we will not have transparency. Or we can choose just the best powder, but due to some issues with sintering process, we will not reach high density, we will have some defects, so again, we will not reach high transparency. So the most important message from me today is that, of course, we can divide our work on different challenges, but in general, we have only one, and the most important, to like achievement of high transparency of our samples. And thank you for your attention. And again, I'd like to say thank you to YCN for this possibility. That's all.
Thank you, Daria, for a very, very nice and interesting presentation. So we are getting to the last part of today's webinar, which is discussion and questions. So once again, if you would like to ask a question, just write it in the chat. And I think in the meanwhile we can start, because we already have a couple of questions here. So the first question is, thanks, Jan. I would like to know how to control the carbon contamination by using SPS and HIP.
Okay, you're welcome. That's a good question. It's I'm not sure if I can answer them in one piece, because in the case of HIP, I mean the main issue is that okay, that might apply in both cases, but for HIP you need to have close porosity, and like that's in principle for HIP you need to have close porosity. And once you do have close porosity, this actually already quite significantly reduces potential carbon contamination. So in the case of HIP, that's usually not a big issue, at least from what I have experienced, what I have seen. Of course, what you can and might want to do is to use, for example, not to place the samples for hipping in crucibles, to place them in powder bed if you really don't believe the crucible. That could also work, so that you avoid, for example, any direct contact. Yeah, that's definitely a good idea. but also to avoid, let's say, exposing the samples more openly to the atmosphere of the furnace. On the other hand, with SPS, that's much more tricky, but it's also much more the issue, because what you usually do with SPS is you put in samples that don't have close porosity. They're mostly powders, pressed compact, and so there it might, like, for a simple powder compact, that might become unavoidable. What you can do, okay, I'm not an SPS expert, so if I say something that's not exactly wrong, I apologize. One thing is the use of sintering aids that actually help you avoid that. And the other is also possibly the use, for example, of boron nitride coating on the whether, for example, on the die, that limits the direct contact with the graphite die. Oh, I mean, you could also, if you're lucky and rich, you could have a tungsten carbide die, and I think this is also less problematic, but there it's really a matter of money. So that's usually not the case. And yeah, I hope that was at least a little bit useful. In case, I think I might have some contacts who might have better answers on this specific question.
Thank you. We also have another question for you, which is how it can be stated that, for example, by using additives such as lithium fluoride or I guess any other lithium additives, how they can enter the spinel structure.
How it can be stated? Well, I mean, it can be stated quite easily. You just do that, right? But in principle, okay, I'm personally not 100% sure there's complete and full and happy, say, consensus on this, but from the general understanding is that lithium fluoride can enter the structure, substituting magnesium oxide. But in general, most of the lithium fluoride will leave actually during the, like, if you use hot pressing, for example, first the lithium fluoride will help you with liquid phase that allows to reassess whether the particles, like, or wet their surface. But then you do have some reactions, but eventually lithium fluoride should evaporate and leave. So you might have some small amount that remains if you, let's say, you don't use some exaggerated amounts of lithium fluoride, of course. And that might get incorporated in substitution of the magnesium and oxygen in the structure. Yeah, so, but I believe the amount is quite limited. I don't have numbers on the solubility, but in general, it's not that much.
Thank you very much. We are now getting into some light scattering questions. So
Nice.
the next question, I believe also for you, Jan, is what is the role of grain size in transparency? Mainly, authors reported that when the grain growth is inhibited, higher transparency is achieved. But for example, by using lithium fluoride in spinels, you can get higher grain size in the micro range, and you can get still higher density. Can you comment on that?
Yes, I mean, here that might be a misunderstanding. I mean, this is secondary. The point is not necessarily that by having small grains you have a better transparency. The point is that if you limit grain growth, it's easier to remove the pores. Yeah. So what you actually want is to get rid of porosity, and it's much easier to get rid of porosity with smaller grains, or especially with grains that grow slower in the, let's say, in the temperature or in the sintering range where you're removing porosity. If, for example, you reached full density and then had afterwards in pore-free material had some further grain growth, that should not really have any negative effects on the transparency. It might have effect on the thermal property, sorry, on the mechanical properties, but then it's not an issue. The point, and that's what you have in lithium fluoride spinels. I mean, spinels produced with lithium fluoride with sintering 8. You can have large grains, but you get rid of pores, and that's the main point. Of course, then if you use a different method, if you use HIP, then generally the grains are smaller, and again you need a microstructure that has relatively small grains and pores at grain boundaries. Then you HIP it, you remove the pores, and the grains remain small. But that is a secondary effect of the process that you use. It's not necessary that you desire to have that. As long as we talk about cubic or optically isotropic materials, of course, if that would be an issue, then you might need to get very, very small, but that's different.
So thank you very much. There's another question regarding the light scattering, and the question is: do the clean grain boundaries scatter the light?
Well, in principle, if they're clean, they shouldn't, right? Like by clean, we mean that there are no secondary phases, that we don't have any phase or area that would have a different refractive index, because okay, if that was the case, then I would expect scattering there. If the grain boundaries are clean, the answer should be no for light. Of course, it would be yes for phonons, for thermal conductivity, but especially if we have material that again is optically isotropic, then it might be a question where exactly the light gets scattered and at the in birefringent materials. One thing that you might actually face is the thermally induced birefringence in cubic materials. So in that case, and okay, again, maybe it's not really scattering directly at the interface of the grain boundary, but there is the effect of thermal birefringence, like thermally induced, birefringence in materials. So even if you have a cubic yttrium aluminum garnet, under certain conditions, it can start to become slightly birefringent, and then maybe it's not scattering at grain boundaries, but the grain boundaries matter because they define the grains that then maybe when they're birefringent, they behave differently. So in principle, no. Under some occasions, yes.
Thank you. Thank you very much for your answers. I think
and I think on this last
Yes.
last point, there actually could be Sonia that could talk much more and longer to sophisticated way on that.
So if there are any light scattering questions, I'm also prepared to answer if necessary. But thank you, Jan, for explaining everything. We have now 2 questions for DARIIA from Nico. Nico, would you like to ask directly or should I read? Oh, mic doesn't work. Okay. So the question is, DARIIA, have you ever tried to use spray drying to obtain dense spherical particles and improve your packing density?
Good question, thank you. I haven't tried for the moment. Maybe in future I will do it. But big part of my PhD thesis was dedicated to optimization of milling parameters and to choosing of raw materials. And we tried milling with different methods, like with roller mixer and with planetary ball milling. And it was found that some conditions gives really fine powders, but as we saw, we have delimitation of samples, and I didn't have just enough time to present everything, of course, but we see quite strong reagglomeration of powder. So in this case, we just choose it's like a compromise, more or less, because of course, if I use spray drying and I obtain like spherical particles, packing density will be higher, but not always some steps are needed if it's possible to produce high dense samples without it. So maybe like in future, just to add like some information and have full picture, it can be done. But in this case, I guess that like it's enough just to know that it can be done without it. Not to, sometimes it's not needed to complicate everything, I guess. But sometimes, of course, it can be pressed well if we just like play more with pressure, maybe, or I don't know, to do pre-pressing with lower pressure, and then like we repeat with higher, or just lower like not so fast do pressing. So I guess it's possible to do it, but like it's not optimal. It takes time and resources.
Thank you, Daria. Yeah, I still remember me trying to use spray dryer in Faenza to obtain some hopefully transparent samples. If I remember correctly, it didn't help, at least not much. And I can definitely say that cleaning of the spray dryer is really exhausting task. So I'm glad you were spared from this. And I have a second question for you, which is, have you ever experienced drying issues, cracks or warping while printing parts with a water-based ink?
Yes, unfortunately, I had quite a lot of issues with it, because specifically my ink, you can dry very fast. So yeah, in my case, it's a problem. But we try to find solution like with adding of some humectant and with like balance between solid loading and some organics, because again, it's like here, as always, it's like compromise, because I can increase solid loading, but it will dry too fast. So I will have a lot of cracks. So in my case, maybe it's better to reduce a bit solid loading. And of course, I will have maybe bigger shrinkage after sintering, but at least I will have full sample, not without any cracks. And of course, like, yeah, it's difficult to dry samples, and like optimization is still needed in this case. Yes.
Thank you, Daria. So we have another question, which is, I believe, a bit more general and probably something we all wonder sometimes. So maybe Jan, Daria, you can answer both. What should we do if the outcome of the experiment is unexpected and the hypothesis fails? How do we tackle the challenges in ceramic exploration?
Okay, I don't know if Peter has an answer. That's I mean, a tricky one. But in principle, you could rejoice because maybe you found something new and interesting. But well, if your hypothesis failed, that's just another step that's not necessary. I mean, as long as your life doesn't really depend on that hypothesis, then it should be actually just a point of thinking, okay, maybe, you know, that there was some parameters that I didn't consider or something like that. Like it's actually a good point to stop and think, even though that's quite maybe not anything new to add, but actually, yeah, how to tackle challenges in ceramics exploration. Well, ideally hand in hand with the available theory and experiment, because it's really that there is already quite a lot of theory available for many mechanisms of what could be going on, but you just, at least my experience is, you just need to follow that also experimentally, because quite often there are some parameters, or there are some points that you might not have considered because they didn't seem that important, and that can be even, like in some cases, purity of the powder, and then you just find out that in your ceramic powder there is this one specific impurity that somehow changes the mechanism of sintering, and you just get a complete different result, and you don't know why. Yeah. And this was like one out of many examples, and so really, I would say after the last 50 years, the theoretical apparatus is quite rich, but it's definitely not exhaustive. Sorry, and so we just still need to experiment as well. I mean, you can estimate quite a lot. I think you can make nice hypotheses, but you just need to experiment for what it is. You know, it's actually a trial. It just it will give you a result, but it might not give you the result that you expect.
Thank you, Hansa. I think that's just stuff we all are dealing with constantly. But sometimes when we are looking at these nice presentations, it feels like, you know, I'm just the only one who is failing. So
yeah, no, that's me too. Don't worry.
right, yeah. So I think we just, you know, sometimes we have to hope for the best, and you know, just try to move on. Daria, do you have any comment on that?
Like in general, I completely agree with Jan, but I'd like to say that sometimes unexpected doesn't mean bad. Sometimes it's something just maybe better, maybe new, and it's possibility to extend your vision, or I don't know. When we like in my case, it's almost always fails. So I know that I have to move on, and sometimes I have to do like step back and just analyze every step of my experimental part. And sometimes it can be just repeated, this experiment, but more carefully, because you just can really miss one small detail, I don't know, and everything goes wrong as a result. But I think the most important is just continue, and to know that like we are not only one who has this problem, because it's common not only in ceramics but everywhere, that science is not so easy.
That's right.
Actually, if I might add one more thing that I think is important and maybe sometimes overlooked, it is actually important to analyze the samples that went wrong. Yeah? It's just, okay, I have a set of samples, and then you look at the best one and say, yeah, okay, this is the one I wanted because these conditions are the best. But you just don't throw away at the moment all the other samples. You know, sometimes it makes sense to analyze them to understand what went wrong or what didn't go as expected, because actually it might be there that you find an answer, and not in a, for example, randomly successful event. Like if for some reason you manage to get a nice result and then you realize you're not able to replicate it, you might need to understand actually what was the difference there. And so, yeah, I think it's quite important to look at the, not only on the good, but also on the bad samples.
Thank you. I think this is a very wise thing to keep in mind. If we can move forward, we have one more question, I think, for DARIIA. The question is, I have another question related, connected to the printing technology, which is partially connected with Nicholas's one. The most problematic part of printing technology is the binding procedure, especially for DLP technology, where we can observe delamination. How do you figure it out?
Yeah, it's a good question. Honestly, I'm not expert in DLP technology, but in general, like if we speak about additive manufacturing and like printing technology, in my case, and maybe if I can give some suggestions, we tried like, firstly, of course, it was analysis of literature because I know which organics I use, so it's quite not so difficult to find like thermal behavior of these organics, like in some already published papers. And just to try with, I don't know, just to try different binding modes with maybe small parts after manual extrusion, not directly after 3D printing when you really have very good, beautiful, perfect sample, and just to put with random mode, of course, of the binding. But also it's quite useful not to use only data from literature, but just to do, I don't know, just TJ of every organic separately, or I mean like the binder or dispersant, whatever you use, and just to understand like thermal history like of this sample, and to know, like, for example, that till 600 degrees C, it should be very slow heating because we see like results of TJ. And we understand that, like, I guess that the best one is really to use results of some like TJ or something like that of initial materials to understand how it can be, which behavior can be during the binding, and then like combine all data regarding like all organics, and I don't know if it's like water or ethanol or something else which uses like oh my god, this word in English, sorry, like which used in suspensions, and just yeah, based on this like thermal behavior of separately part, try to find optimal conditions for ready green body. I'd worked in this way.
Thank you very much, DARIIA.
Yeah, I think on that, maybe just one more thing, or one. In general, okay, if you observe delamination, if you manage, yeah, and that's not easy, to further increase the solid loading, that might help because you compensate for the amount of organics that you need to burn out. And if you do have delamination, as DARIIA said, then probably you have too much, like at a certain point of your debinding, you have just too strong evolution of gases. So, okay, if you identify that point, you might want to go slower there, or you can use less atmosphere that's less rich in oxygen. I just try to reduce the oxidation in this way.
Oh, and sorry, if I can add, probably it's also important to figure out with drying before the binding, because we can have small minor cracks not really visible by eye but then after debinding with a bit like temperature, with process, with gases, it can be, we can have big cracks as a result from those small. So also it should be optimized everything together, not only one process like debinding.
Thank you for a really exhaustive answer. So I would like to ask if anybody of you has any other questions, just write it down in the chat. And in the meanwhile, we have this question if you could share a copy of your presentation for educational purposes. I would like to mention that this webinar is being recorded, so it will be available later on YouTube, so you can always rewatch if you want. And maybe, what do you guys think? Maybe if they could write you directly?
Yeah, I think that'd be the easiest thing. I might just need to check if there's something that I shouldn't be sending out, but in principle it shouldn't be a problem. So yeah, if you write to me, I generally tend to answer, and if I don't answer, please write to me for the second time. I will.
All right, thank you. So, any other questions? So, if not, I think we are ready to conclude the webinar. Thank you guys for joining us. Thanks to both amazing speakers, and I hope that we will see each other very soon again. And have a great day. Bye-bye.
Bye. Thanks for having me here, and thanks for everyone for participating.
Thank you. Thank you. Ciao.
Thanks, everyone. Bye-bye.
Thank you. Bye-bye. Okay. See you soon, Sonia.
Okay.
Bye-bye.
See ya.